Get started. Hi, everyone. This is Jason Key at SB Grid at Harvard Medical School. Thanks for joining us today for our webinar. For today, we're going to shift back to back to the NMR. And talk about PDBStat. Maybe not necessarily NMR per se, but today we've got Roberto Tejero joining us from Valencia. So Roberto did his PhD in Valencia. Then he crossed over and did NMR in Pittsburgh and at Rutgers for a few years, where I think he developed his interest in biological molecules. He's a professor in the Department of Physical Chemistry at Valencia, and he's the author of PDBStat. So he's going to tell us about PDBStat today.
Okay, hi everybody. I hope this goes good because I had a bad day. I grew some fever from this morning. So let's say we are going to talk about PDBStat, and as the slide says, it's like centering on features for NMR structure and constraint satisfaction and analysis. The software is described in that paper that is Journal of Biomolecular NMR, published in 2013. Okay, as a very short introduction, it started like a translator between uh, different formats, coordinates and constraints in the old times. Actually, I had some Disman structures with all those terms for correction for the constraints like P, Q, R, S, whatever. So I started to develop some software just to transform that because we wanted to do some molecular dynamics refinement with Conjig, with this program. And that was the beginning. Then it evolved into a tool able to perform some statistics analysis, mainly what people ask me to do. And lately has been a lot of use of it, just converting from different formats like Sayana to CNS for doing weather refinement or explore, and then to Rosetta, and then the last format, the NMR exchange format that was published this last year, 2015, and is not included in the version that is already on the web page, but it will be in the next version. It's already tested, and it will maybe need some corrections by hand, but it will mainly do the job. Another characteristic is that the engine running a software that maybe you know, the auto structure and PSBS analysis from Rutgers University, the NMR lab at the CABN, the protein structure validation server. So usually performs underneath some tasks like whatever coordinates people send to the PSBS, it will be pre-processed by PDBStat to prepare all the analysis. And it is commonly used also to help in setting the files. I mean, just creating the needed files into CNS to do water refinement with CNS mainly. And the other use is like a standalone or interactive mode where people can do some analysis. Some useful task or information is described in this web page that either I will try to do something, I will show you here. So you just go to the web page and click here in PDBStat, and you have something there. Don't be afraid about the Spanish because it will be written in English, the part that is needed. Okay. So another characteristics is mostly written in C and with some parts in C++ and even tiny amounts of code in Fortran. Usually, the binaries that they are accessible from the web page, they are mainly on Linux and lately in Mac OS X. Actually, lately I have a Mac, so I am developing the software in this platform and then compiling or making sure that the results are the same and that everything compiles properly. And even I did some version for my students in Valencia for those Windows using Sigwin, whatever, so they were able to use the commands. The other main feature is that it's text mode, so I'm sorry, no graphics at all. Just to make life easier of people, the program is able to do some command line editing with Redline library and some most of the commands and options accept abbreviations, usually to 3 letters, where there is not ambiguity in those 3 letters. If not, the program will tell you something. And it can be used either interactively, that is the, at least at the NMR lab at CABM is mostly used, or batch processing for the PSBS. So you can write a script with the commands of PDBStat, and you will use the -s flag to make PDBStat able to accept the batch processing. If not, it will crash badly if you don't use the -s. Okay, so in order to explain some of the commands and centering about the like analysis of structures coming from NMR, I divided the commands in either coordinates related or constraints related. For the coordinates related ones, I guess the most important or the most useful, somehow they are expressed in this slide. So it will be determine or express or find the well-defined regions estimation for an ensemble of models. I mean, usually one gets 20, 10, 100 models out from a structure determination program. So these commands will be able to provide you with a range of well-defined regions estimation to do the best superimposition for the atoms. So in this order, I will explain like slightly like the order parameter or the fine core algorithm and the expanded fine core, that is the last one we developed to help in this process. And here on the right and in font courier, it will be the commands that they are available inside of the program. The other ones are like fixing or checking the stereochemistry. I mean, sometimes, due to the fact that we are doing simulated annealing with molecular dynamics, some of the atoms can get flipped and some bad stereochemistry should appear. And also, some programs like Explorer and CNS is well known that they use different labels. So this command, fix stereo, will fix the right atom names, the right labels. Then the other important part is superimpositions, r.m.s.d or root mean square deviation calculations, or either hydrogen bond estimation. I mean, there is a lot of software that it will do like better job than PDBStat, but it's handy if you already loaded a set of models that you can use those commands. And the other part, for example, is also like instantaneously you can get an estimation of Ramachandran scores, either with ProCheck. You will get similar, if not the same results, because I use the same grading for the maps, or another command that is called evaluation of Rama. This uses the Richardson map, so you get slightly different results. I will show you in a slide. And then just processing or doing some contact maps, either from coordinates or from constraints, to compare and gain some insight into the results. In order to calculate the well-defined regions, PDBStat is able to locate these areas and inform you using like several methods. One of the first one that it was implemented is the so-called dihedral angle order parameter. We call DAOP. It's defined by Sven Heiberts in this nice paper from 1992. Basically, it defines two order parameters, one for phi and one for psi, for all the residues all through the models. That means from the n models in the ensemble of conformers. If they are properly defined, I mean, it's the same model repeated 20 times, you will get all the parameters of 1. And as soon as the angles, they don't look similar, that parameter will go out of 1, getting to 0, like quickly, like rapidly. So in PDBStat is this command called order 0.90 that it will calculate automatically the changes that include all the residues, for example, which order parameter for phi and psi greater than 0.90. Also, one can use like the convention that if the sum of the order parameters is greater or equal than 1.80, that means that the whole residue I is taken in the well-defined array. And then the most important part is that the program will remember this order, this well-defined region. So any further r.m.s.d superimposition calculations, it will be applied only on those ranges, forgetting about not so well-defined arrays. So as an example for the DAOP method, if you type inside PDBStat order 0.90, it will show you something. I edited this file. It will show you all the order parameters for all the angles, but it will show you whatever is greater than 0.9 for both phi and psi. And then at the end, it will provide you with the ranges of residues that fulfill that information. And this range, it will use for further superimpositions. So soon it was realized that the dihedral angle order parameter is not so well devised to get the well-defined regions. For example, imagine the case you have two domains and they are flexible with one respect to each other. So you will get poor dihedral angle parameters. So a colleague of us, David Snyder, developed and is included in the code also the fine core algorithm. Usually it will calculate the core residues based on the interatomic distance matrix and doing some mathematics with it. And for example, it will provide these results, the original core. Then we realize that this information, as you see, is done like for the same model as before, the same example, and it get two ranges instead of only one. And it's because it's too, I guess the English word is stingy. So it was like really picky about including one residue or not. So we came this, in order to publish the paper, with another method that is the same thing. So first the algorithm will calculate the core atoms and then it will expand them, calculating the standard deviations and expanding the code accordingly inside. And for example, here you have, after the expansion of the original code, whatever you get, and it's the same mostly like with the dihedral angle parameters. And also it will match another results like the side range method to calculate the range of the atoms, mostly. Fixing the stereochemistry, it was done in this way. I mean, here I can tell you a comment like the referee told us. We could calculate that with the differences between the dihedral angles. But anyway, in the code it was included this mathematical way. And here is an example. I will explain this this figure. We have two names, HB3 and HB2, and one of them has to be HB2 and the other one HB3. So sometimes, or some programs, they change that names. In order to fix that, what we define is like two vectors, the C alpha to C beta, the C beta to C gamma, and we determine the plane through the dot product. And then it turns out that one of them is up the plane and the other one is down. So we can calculate another product and discover which one is on top or the other. So what the program does is this. So it will change only the labels, not the coordinates, because it's a matter of the labels. Once all the betas are fixed, it will go gammas, epsilons, deltas, etc. And every residue that means actually that kind of checking. Another command that I explained to you is like also is able to calculate or to estimate the possible hydrogen bonds in a molecule. Here a comment, it will do whatever it has hydrogens, or if it comes from X rate, it will calculate also, it will estimate the possible hydrogen bonds. Usually the default values that it uses is that for that distance between the donor and acceptor is 3.5 angstrom. Sorry, and 120 degrees. And oops, oh, sorry. And the other command that is we find like it was in Sayana present. It is really cute. We provide this H bond all. It will calculate automatically an estimation of all the hydrogen bonds, and it will provide points whatever is present in any model of the ensemble. That usually it helps also to check on some hydrogen bond constraints or some NOA constraints. For the r.m.s.d calculations, as I told you before, once the well-defined regions are done, the user will use this command, r.m.s.d best, either backbone or heavy or whatever. And this best, it will make the program to remember whatever it already defined as the range, the well-defined range, and it will provide you the r.m.s.ds for every single residue and then some averages at the end. This is an old slide, right? In the last one, in the last version that I am working, here it will show up an asterisk pointing to the MEDOI or most representative model. So it will provide you also with the most representative in the sample. For the Ramachandran scores, and just to show you what I commented before, you have these two ways. One of them, the eval project, it will evaluate the same values as I was telling you, mostly the same as project. And then eval Rama, that it will provide the way the Richardson provides, Richardson and et al. It will give you the most favored area or percentage, and then it will divide either in allowed or in outliers, and it will point to the values. As you see, they are slightly different, and this is because they use different mappings, different considerations for every residue. I guess people tend in all our meetings to believe more these things, but anyway, you can do this better with the Richardson software. The only thing is, once you load those PDB files into PDBStat, we thought it was handy to have this application. I mean, as you see, most of these models or these features come from friends asking at the lab whatever they need on a day-to-day basis. Also, it will provide you some information about the models or just that you're aware, like the number of atoms, like the number of residues, molecular weight, the radius of gyration made out of the coordinates, and so the so-called, following a paper, the estimated radius of gyration. As you see, they are usually different, and that is the reason it's used for some of the structural refinement, and it will provide you also the sequence and the number of every residue, the different numbers. Well, that is regarding the coordinates. What about the constraints? For the constraints, the most important features is like the analysis or the constraint satisfaction, and also making the contact maps that I will go. So one of the features is that Lately is able to read all the all the distance angles, the hydral, RDCs, whatever is in a single file. This came also asking from friends, because a PDB file usually provide a file.mr that holds all the restraints. So it was good to have this. So the parser that is inside the program should be able to determine the different classes and classify all the constraints. The analysis, it will be done on the reading step, making sure that they match sequence and they match atom labels. And then I will explain some commands that, like for cleaning, that means removing or any of meaningless, duplicated, or missing, no, wrong anyway. Meaningless mean that sometimes there are a few or more than a few of NOIs that they are not really useful, because they come determined by the geometric stuff from the residue. So the program will locate those ones and then will remove. So in order to do the constraint satisfaction, that is, I guess, is the most useful feature. I mean, you just read the coordinates, you just read a set of restraints, and you want to see how the constraints or restraints just match the coordinates. The best way to do that, it will do in several steps. The first one should be like the cleaning, just avoiding the meaningless or duplicated ones. The word is like no clean, so it will clean all the constraints. Then, in order to avoid mistakes that I can show you later with some commands on the screen that I prepared for you, we convert everything, coordinates, to IUPAC atom labels, and all the NOA to IUPAC, just to avoid conflicting times. And then the command to calculate the satisfaction will be, we want to see the violations of the restraints applying the sum average. And here, I mean, there are several averages. I guess everyone is aware of that. If no, the program can apply like the center, the sum. The sum is actually this one, and this is the most useful for us. it will calculate all the distances, the inverse of all the distances between every two pairs and calculate this kind of average, and then the constraint map. So if you apply, for example, for this, I did this application for two models just for you to solve. For example, for the 2L9R that you can find at the PDB database, you read the coordinates, you read the constraints, you apply the cleaning, and then no, sorry. This is only like a summary of the constraints, not the constraint satisfaction. I'm getting. Oh, here. Here, this is just a summary. Another feature that people ask me is like you read the constraints and you want to see how many are the total one, how many are intra, how many are sequential, and then divided in backbone, sidechain, sidechain, sidechain. And this is the summary that you can get with this command, NOE analysis or analysis itself. So it will provide you with this, whatever is in the memory, it will classify either the distant restraints, if they are ambiguous restraints, or the dihedral angle restraints for this example, or for this other example. So you see, as more and more constraints are present in the file, it will keep adding fields with all the classifications. I hope I am explaining myself right. Sorry. So if you have more than 5 inside, you have Chi1, Chi2, and other Chis, like in this work that people was doing over this structure. You can get all the dihedral and even residual dipolar couplings also. Everything will be classified, hopefully. This is the analysis of constraint satisfaction, sorry. So I will apply this to 2L9R.pdb file. Okay, so as I said, it will be read coordinates PDB 2L-R9. Read constraints, CNS, because they come from CNS, or explore is the same format, 2LR.mr. You won't need this one because as all the constraints will be stored there in a single file, it will break them up. So then you clean the NOEs, then convert everything coordinates to UPAC atom labels, and then NOE to UPAC atom labels. You set up a cutoff for the violations, and then you see the violation. And you will get a file like this one. I hope you feel, or you can read the numbers. Basically, it will provide you with a list of all the violations greater than the cutoff, then a summary of those violations, and then whatever people ask me, like the range 0.1 to 0.2 angstrom, 0.2 to 0.5, and greater than 0.5. It will classify, and then different kind of averages for the all intra, sequential, medium, long, etc., and the minimum and maximum violation. If you don't provide a cutoff, the program will use a 0.3. That is the whatever we came with the besting. And this also was asked for from some people at the PNL labs that they needed to do, like it was like huge amount of models, and they wanted to see all this general global summary for all the models. So you can play with this one, and you can distinguish. It will point you whatever violation is really big. It will point you which one is, so you can go back and forth between the NOE file and locate that restraint and make sure that it's okay or it's not okay. The contact maps, it was another feature developed just to check on the restraints. For example, you have here a contact map made from coordinates for the same structure, and then from the constraints. Okay, so if you see the numbering, it was a table. So that means the first chain and the second chain. Here, the first chain and the second chain. And then the comparison that everything were mostly okay. And then the NOE was like pretty good. I mean, reproducing a lot of the features present in the contact map made from the coordinates. The other important part, as I was telling you, is the conversion, so translation between the different formats. Coordinates, as I was telling you, usually that means just to adapt the atom labels or names, because every program lately uses like the PDB format to write the X, Y, and Z coordinates. The only thing they modify is the atom labels, because everyone uses different atom labels. So the first thing after reading the coordinates will be coordinates to UPAC, or just avoiding coordinates to CNS, to Explore, to Sayana, to Rosetta, because these ones, they use different atom names conventions and this one. These CNS and Explore use the same, but these ones, they use like HB1, HB2 in this case, and then HB2, HB3 in this case, and this again HB1, HB2, but different from this one. So whatever is HB1 here, here is HB2, and that is the reason of using the fixing stereo command. And for the constraints or constraints is the same thing. Once you read the constraints, you will say NOE to Rosetta, or NOE to CNS, or NOE to Sayana. In this case, it will not only convert the atom names, but it will adapt also to the special formats. I mean, Rosetta format is different from Sayana format, and is different from CNS with the assigned keyword, etc. So all this will be done. Before I introduce you to this slide, I want to comment you one that I forgot. I realized just now. The other important feature that I can show you in the discussion coming later is that it's able also the PDBStat code is able to calculate the NOE completeness based on whatever is published. I mean, it will read PDB coordinates, it will read some constraints in whatever format. You will issue a command taking NOE complete, and it will calculate with a series of defaults the percentage of completeness between whatever is in the constraints and whatever can be deduced from the coordinates. That I believe is like really good sometimes to see the degree of how the NMR experiments came to provide with you with the constraints. So the current status, it will be like, I wanted to mention that it will handle directly Sayana dimers. It will locate the protein to linker, the linkers, and the linker to protein, and it will make different, it will create chains depending on these keywords. So it will provide like a file ready to be used like by Explore or CNS or the others that they don't use those linkers. In general, it should handle properly XMERs. I mean, one of the files I was showing you, the 1ZLL, is a pentamer, I believe, and it reads pretty good and it calculates everything. This one. So the other current status is, like I told you, it will read all, whatever is stored in the .mr file at the PDB. I mean, hopefully, when I say all, it will calculate and it will classify all the restraints in that. RDCs were before read but not dealt with. Now you can analyze and obtain like the DANR, the axial and rhombic component using eval DAR. I mean, there are other software like PALES and all the others to calculate that, but this you will get the same values, the same. I mean, I apply the same method, the single value decomposition, and it's handy just to have this and calculate from directly from the RDCs. And then this feature that is the one coming, it's able to read and write in NEF, the NMR exchange format, the latest format. That, well, I forgot to comment. I guess you are aware of this. Whatever one translate between Sayana, Explore, and the others, you end up missing some information. And every translation you do, because there are different formats to analyze the lower bound, the upper bound, the target value. And people were developing this software, this new format, to make sure that no information is missed in all the translations, so that it will hold all the information together. It's basically whatever it is. Other features that I am not going to tell you is, for example, able to classify the models by energy. I mean, somehow you are able to put the energy coming out of the CNS, Explore, or whatever model, the target function, in remarks records. It will look for those records, it will extract the energy, the keyword, and it will classify the models based on the energy. Another feature, like another friend, like James Arabini asked me, it was the once it's done doing some orientation, he feeds, he stays the nice orientation he wants the coordinates to have. So he was doing that with, sorry again. So he was able to do that with mobile. So he wanted the software to read the transformation matrix and apply it to all the coordinates. And I did that also. I mean, it's a lot of features that maybe they are not well documented. I am trying to document better all that stuff. And we are reaching to the end of the talk. There are some tricks to keep it running that all over the times people is asking me. The usual installation takes place here under user local in every machine, either the Mac or the Linux or whatever. So there are two main files in the libraries for PDBStat. They are called the Jenkins lib and the PDB Keywords. So sometimes if some new PDB keyword is being used, the program will stop because it won't recognize that word. You just edit that file, add the new keyword, and you are able just to continue. So you can edit by hand. You don't have to recompile nothing. And then assume you have like some special atoms or residues. You just go to jenkins.lib and you edit accordingly just to create whatever you have in your residues. I will show you now some examples. For example, in this case, for another friend, Paolo Rossi, he was using some system but he modified the Sayana library to have a sync inside because it was a modification. So you just go remove this and just create this sync file, and PDBStat will know from there that that system, that special system, can have some sync files. So it will be worked out. And another example is like we were working with Norlucin and our studies in Valencia. Another team was working in this. So I did creation like this. Well, these columns that they are repeated is because it's this man, Diana, Sayana, Explore, CRS. I mean, I produce all the names for every possible file like Rosetta or whatever for the future. And then for some metals also, you can add whatever metal is present in your protein and it is not covered, you will add here and it will be used from that moment on by PDBStat. And the PDB keywords, just to show you an example, this it usually has a subset of whatever is accepted by the PDB database. But then, for example, I noticed that if people were using Mage for the program, it adds some user keywords, so I have to add this. So every time I find a new one, I mean, if the software refuses to read that, you just, okay, whatever it's complaining and add the word there and that's it. So yeah, so I will be glad to take any questions.
But yeah, if anyone has questions, feel free to, you can go ahead and chat those in the chat window or send them to me. I'll relay them. Thank you very much, especially for going through it with a cold, which I know can be tough. So I think anybody who's done structured determination with NMR knows how painful it can be to have to jump between different programs, particularly with IUPAC names and jumping between different constraints and restraints. So documentation, your website is sort of the go-to source. Would you say that's correct?
Yeah, let me see. It shows here. It shows in the screen the web page.
Yep.
So you could see it's a description of some useful tasks. It's an online manual, but it's not well done. And then a friend of mine, James Aramini, did this wiki that is in the NESG consortium, and it will also show you some examples about how to do some regular tasks like reading coordinates, classified by energy, whatever. So he was an advanced user, so he was writing all this thing. But the way to do is here, or just send me an email if you need something. I am trying to complete that. So the useful task, for example, is like fixing the labels, the atom names, like calculating the well-defined with the dihedral angle parameter, or with core only, or just with the expanded core. The NOE completeness, whatever you need, is also there.
That's fantastic. That's really great to have a nice tool. I think a lot of NMR labs, I've seen lots of scripts around that are sort of, bits and pieces of these, and they're not particularly rigorous. So it's good to have,
Yeah.
a solid tool to use.
Actually, I forgot also to mention that what people use the most at the NMR lab at CABM at Rutgers, they usually produce the structure with cyan, and then they wanted to do the water refinement. So it's like a set of scripts like here at the water ref that it will call PDBStat, and it will produce and convert all like the upper bounds, lower bounds, the hydroangle constraints, RDCs to the CNS, and then it will provide you with the scripts to do that refinement, hopefully automatically, with little manual intervention.
That's great. Well, with that, thank you very much again, and I hope you feel better. All right, well, thank you.
Okay, you're welcome.
Bye.